Hi, everybody. Welcome back to asymptotics and perturbation methods. So today we're going to finally begin our study of perturbation methods for differential equations. We recently started talking about perturbation methods for algebraic equations as kind of a warm-up. And of course, we spent much of the earlier part of the course doing asymptotic methods for approximating integrals having small or large parameters in them. But finally, we really get to the heart of the matter, which is using these techniques and developing new techniques to solve differential equations. We'll be focusing mostly on ordinary differential equations, though towards the end of the course, we might also get into a little bit of partial differential equations or even difference equations where time or space can be discrete. Okay, but let us jump in. All right, so I want to start with sort of the vanilla version of perturbation methods. These go by the name of regular perturbation theory. And we'll see what's regular about them in the course of our work here. But I thought maybe the clearest way in is to just do a concrete example. All right, so let's start with example 1. It's a projectile problem, sort of the kind of thing you would have seen in a classical physics course. Excuse me, just want a little more light here. Yeah, okay. So suppose you've got a little toy rocket and you're gonna blast off the surface of the Earth and go straight up. That rocket is gonna go up a ways and then come back down and hit the ground. And our question is to calculate the motion of the rocket and also to specifically calculate how long will it be in the air. How long does it take to go up and come back down and hit the ground? Now, that, of course, is a very easy problem discussed in a first-year physics course. But usually the assumption is made that the acceleration due to gravity is constant. Now, that's true if you stay very close to the surface of the Earth. But what if we take into account the fact that the strength of gravity weakens slightly as you go higher and higher because you're farther from the center of the Earth? That is going to be a tiny correction for a toy rocket ship, which is not going to get up very high compared to the radius of the Earth. Nevertheless, this is a kind of thing we can do in perturbation theory, calculate the correction to the standard solution by allowing for the fact that gravity does get a little bit weaker as the rocket gets higher. All right. So that small change is what we would consider a perturbation to the traditional problem, a tiny correction. All right, so let me write out Newton's law for this. It would look something like this. If we're going to write F equals ma, so ma would be m in the coordinates I'm using, where x is the distance from the surface of the Earth. That's shown in this little diagram. Ma would be mx double dot, so dot meaning time derivative. And so the force is given by Newton's inverse square law, so minus g, big M, the mass of the Earth, little m, the mass of the toy rocket ship, over its distance from the center of the Earth squared. So that would be r plus x, all squared, here r being the radius of the Earth. Okay, so that's our equation, and we can clean it up a little bit. Notice that I could cancel out the little m's. And it's convenient to write this by multiplying and dividing by capital R squared, like so. So minus g, big M, all over r squared, times r squared on the top, over r plus x squared. And the reason I'm writing it like that is because this first term that involves all these constants, that's the familiar quantity that we call the acceleration due to gravity. So that would be minus little g, big R squared, all over r plus x squared. Okay, so that's x double dot. Now, reasonable initial conditions for this problem would be, we're starting at the surface of the Earth. So initial conditions which for the rest of this course, I will occasionally tend to abbreviate that as just ICs, initial conditions. The initial conditions would be that at time 0, let's start the clock when we release the rocket, launch the rocket. So x at time 0 would be 0. It's on the surface of the Earth. But what about its initial velocity? Well, of course, that's not 0 because we're blasting off, we're firing straight up. So let's call that some parameter V0, the initial velocity. And we're thinking of a toy rocket. So this initial velocity is going to be small compared to the escape velocity. I mean, we're not going to launch the rocket so that it goes into outer space. It's a small quantity compared to the escape velocity for the Earth. So let's formalize that as follows. We're going to assume the initial velocity is small in some sense. And part of what we want to do here is clarify, what does small mean? You know, throughout the course, we've been talking about small or large parameters, but in real physical or biological or financial problems, small always means compared to something else that has the same units. So here, small has to mean small compared to the escape velocity. Another way we could think about this small quantity is that the height that the rocket is going to go has to be small compared to the radius of the Earth. So these are, you know, in a real application, you'd have to sort of monkey around a little to figure out what is the right small parameter. And so I want to illustrate that with this problem. Anyway, so we're going to assume the initial velocity is small such that, as I say, the distance above the Earth is going to be very small compared to the radius of the Earth at all times. Okay. So naively, I mean, if you just look at the equation, let's sort of go to the lowest order of approximation. Let me put this governing equation in a box here. Let's focus on this. Right. So naively, thinking of our quantity x as being negligible compared to r, right? If I could ignore this x compared to this r, then I would just cancel out the r squared in the top and the bottom, and we would be left with x double dot would be approximately just negative g. And that's the usual move in first year physics course. So if we did that, then we would have a simple equation that we could integrate twice, and we would get x of t is minus 1/2 gt squared. And taking into account that there's an initial velocity would give us v0 times t. I'm skipping some steps there, but I know you know how to integrate twice and use those initial conditions. So that would be the standard solution. And you know, if you wanted to visualize it graphically, you could draw a picture like this. We could show x versus t. So we're keeping track of how high is the rocket as a function of time. It's going to go up and then come back down. It will make a parabola. Now this parabola is not, I'm not talking about a trajectory going sideways. I just mean x as a function of time. Also coincidentally looks like a parabola. You could check that the maximum height that will be reached is V0 squared over 2g. We could get that by setting the derivative of x to 0. It's going to be when we're at the top of our flight. And that will occur halfway through the flight, which will be at a time, it turns out to be V0 over g. And the time to hit the ground in this traditional problem will be twice that, 2V0 over g. So those are little things that you could check just by working on this formula here. But what we're really interested in is the corrections to all of these results that come into play when we take into account that gravity is not actually constant. Little g is going to be corrected slightly. So that's our question. Find the leading correction, the most important correction to all of this, to this solution. And, you know, again, when does the particle hit the ground, the rocket hit the ground? Okay, so let us scale the problem to clean up the algebra a little bit. This is always a good move in a question like this. It's best to work with dimensionless quantities if you can. So when I say scale, what I mean is I'm going to think of the characteristic scales for both x and time. Our picture above actually shows us what those characteristic scales are. You could think of it this way: a characteristic scale for the time, so I'll call it TC, and for the upward distance traveled XC. Well, they have to be something that have units of time in terms of given parameters in the problem, the V0 and the G. So we're going to get that the characteristic time, let's call it V0 over G. You can see from this that was like halfway through the motion. And a characteristic scale for XC, or characteristic XC, would be given by this height. We're actually, since I don't feel like dragging around factors of 2, I'm just going to ignore that and say XC, let's suppose, is just V0 squared over G. I can define the XC and the TC any way I want, really, as long as it has the right character. So it's simplest to omit those factors of 2. We got that, and we got that. And let me now rewrite everything in terms of those characteristic scales. So I'm going to define a dimensionless time, tau, to be t over the characteristic time. And I'll also define a dimensionless altitude or distance y to be x over its characteristic time. And as I say, this doesn't change anything. It'll just make our algebra a little easier, a little cleaner. All right, so these are dimensionless. Okay. Next, let's rewrite our governing differential equation in terms of those. So the differential equation had second derivative of x in it. So let's calculate some derivatives. The first derivative, x dot. We know that that means dx by dt. And so in terms of these new quantities, x is a constant xc times y, and t is tc times tau. So as you'd expect, those constants come outside to give you something with units of velocity times a dimensionless quantity dy by d tau. Xc over Tc, we can combine to simplify things a little bit, I suppose, if we wanted to. We'll get something that has just a V0 out in front. Actually, let me do x double dot while I'm at it. So x double dot will come out to be, skipping a step here, you'll get xc over tc squared, which has units of acceleration, times the second derivative of y with respect to this dimensionless time. So putting everything then into the differential equation, or ODE, the ordinary differential equation, that's how I'm going to refer to this expression up here. This is my ODE. That ODE will become xc over tc squared, second derivative of y, with respect to tau, is minus g r squared. And then in the denominator, I had r plus x all squared. So x, we know, is now xc times y. And there's plus an r. All that is getting squared. Okay. And there, it's kind of nice to divide through by the r squared in the top and bottom. I'm trying to get my equation to be dimensionless. So let me try to cancel out as much stuff as I can. This would be minus g over quantity xc over r times y plus 1. All of that stuff squared. It's getting a little nicer. Now, actually, this expression right here, if I look at that xc over tc squared, let's see what that would be. I mean, it has to be units of acceleration. So it's got to be g, doesn't it? And this is going to be v0 squared over g. That's my xc. And then the tc squared in the denominator would put a g squared up here and a v0 squared down here. So the whole thing is g. Right. So it's what we would have expected. That we're now getting g times this second derivative of y with respect to tau is minus g all over xc over r, y plus 1, all squared. Can cancel out these g's, doink, doink. And I've now succeeded in cleaning up the equation a lot, right? I mean, it's now saying, maybe it's sort of tempting to use prime. I don't know if we should. Let's use prime for tau derivative. So I have y double prime is minus 1 all over, I'm going to call it epsilon y plus 1 squared, where you see my epsilon has now very naturally emerged from all the non-dimensionalizing. Epsilon is this ratio of the critical or the characteristic distance, characteristic altitude that the rocket can reach compared to the radius of the Earth. We said from the beginning, we're going to be interested in the regime where that is a small quantity. So that's why I'm calling it epsilon. So there's my nice non-dimensional version of the ordinary differential equation. Okay, and so now we want to do perturbation theory on that. Incidentally, you can also write this epsilon in terms of the original quantities in the problem. If we look back at xc, the way we had defined the characteristic, x v0 squared over g, that gives us an interesting expression. We get epsilon is v0 squared over gr, which you can interpret as saying that the initial velocity is very small compared to the escape velocity. So it's all working out the way we would have expected. Okay. Now, let's also convert the initial conditions into this new dimensionless way of looking at things. So the initial velocity, or sorry, the initial position was in this dimensionless form, we'd call it y0. That would be the actual x0 over xc, but that's just 0 over xc, so 0. So we're starting at y equals 0, and the initial velocity in this dimensionless setup, dy d tau at tau equals 0, that would be tc over, well, x dot at times 0 over xc. Skipped a step or two there, but this comes out to be v0 tc over xc. And if you look back at my definitions of all of those, that's actually going to be 1. It's pretty beautiful. I mean, we knew it had to be something dimensionless, but it comes out to just be 1 in this way of doing things. So we don't have to drag around all those parameters with us. All right, so now we're just solving the problem where we have, like I say, our initial position in the y variable is 0, and the initial velocity is 1. So we've boiled everything down to solve this system, or this little dynamical system. Y double prime is minus 1 plus epsilon y all squared, subject to the initial conditions. Y of 0 is 0, and y prime of 0 is 1. That's our new version of the question. Okay. Okay, so how to solve something like this? You'll notice it's a nonlinear equation, actually. Got this y appearing in the denominator. We're getting a y squared. It's not super trivial to solve this exactly. It might be possible to solve it exactly. I'm not sure. I'm not going to do that. Instead, I want to solve it with perturbation theory to illustrate the method, where the whole point is that we can exploit the fact that epsilon is small to look for a series solution of this in powers of epsilon. That's the idea of regular perturbation theory. So we will try to solve this by assuming that we can write y as a function of tau and epsilon as a power series in epsilon. So that's the most basic thing that you could do in perturbation theory. That's part of regular perturbation theory. So we're going to write down this ansatz, y tau epsilon equals y0 of tau plus epsilon y1 of tau plus epsilon squared y2 of tau, and so on. Or we can just go as, take as many terms as we care to take. All right, so it's a power series in epsilon with these functions that are themselves, the coefficients are functions of tau. All right, and the beauty of this is that when we pop that into the differential equation, the initial value problem written down up here, we're going to convert this nonlinear problem into a series of linear problems, which are much more tractable, but very easy to solve, actually, using standard methods from a first, really from a calculus course or a first differential equations course. So let's take this and plug it in. Oops. Getting a quadrilateral there. So plug that in. We also have to convert the initial conditions in terms of these new variables, y0, y1, and so on. So we can do all of that. But let's see, is it time to do that yet? Yeah, we might as well while we're thinking of it. So what would happen to the initial conditions? And then we'll see what happens to the differential equation. So the initial condition we know is that at time 0, y of 0, well, that'd be y0 at 0 plus epsilon y1 of 0. And actually, I'm not going to keep the epsilon squared term, so I'll just write plus dot, dot, dot. We'll only do this to order epsilon. So what is that supposed to equal? That is supposed to be 0, we said above, right? That's right here. So the way you have to interpret an equation like this is that it's supposed to be 0. Both sides are power series in epsilon. This is supposed to be a statement that's true for all epsilon. All right, this is supposed to hold we're thinking of epsilon as small, but it's supposed to be true as a statement of power series in epsilon on both sides. And so in order for that to be true, you then can equate the coefficients of like powers of epsilon. A move that we'll be making throughout regular perturbation theory. And actually, even when we do the more sophisticated thing, singular perturbation theory, this same kind of move will come up. So read off, I mean, this side of the equation doesn't look like much of a power series in epsilon. It's the 0 power series. All of its coefficients of all powers of epsilon are 0. But here we could read off the constant term that this one has no epsilon in it. So we get y0 of 0 is 0. And now also reading off the coefficients of the epsilon term on both sides. Well, here it's y1 of 0. And on this side, it's still, there's the coefficient of epsilon is 0. So that's also 0. All right. So anyway, we've got those initial conditions. And we also need to take into account the velocity initial condition. Remember, we had this, y prime at 0 was 1. That's going to be a little more substantive. So not much, but a little more. So y prime at 0 equals 1. That would correspond to y0 prime plus epsilon y1 prime, all evaluated at 0. So reading off the different like powers of epsilon again, you see what's happening here is that the order 1 term, that is the ones with no epsilons in it, would give us 1 equals y0 prime at 0, whereas the order epsilon term would give us, there is nothing here at order epsilon, so we get 0 on this side, whereas here at order epsilon, I have y1. And these are all evaluated, I should say, you know, at time tau equals 0. So I'd have y1 prime at 0 is 0. Okay, so those are what our new initial conditions become. Maybe I should put a little box around them. Got that, got this. We'll be invoking these later. Okay, so far? All right, but now the real action is converting the differential equation itself. So let us do that. We're plugging, remember, this expression into this differential equation. And we're going to, again, group things according to powers of epsilon. So let's do that. I'm going to need a new page here for more calculating. Maybe I'll add one more just to be on the safe side. Okay. Oh, those didn't get added where I wanted them. So let me move this down here. Okay. All right, so the ODE let's see what that becomes. So remember, it was y double prime is minus 1 all over 1 plus epsilon y squared. So with the series assumption we've been making, plugging that in, on the left, we'll get y0 double prime plus epsilon y double prime plus ... The stuff we're neglecting is, think of it as minus 1 plus epsilon y to the minus 2 power, which you could write with the binomial theorem as minus 1 minus 2 epsilon y plus order epsilon squared stuff that we're neglecting anyway. So this would be cleaned up to just minus 1 plus 2 epsilon y plus ... And now we substitute for the y. So 2 epsilon y0 plus epsilon y1 plus ... And everything is with an order epsilon squared garbage pail that we're not filling up. So anything that's order epsilon squared, we're neglecting. And so when you multiply out, you can see I've just generated such a term. I have a 2 epsilon y0, that's order epsilon. I want to keep that. But the next term, which would be from this 2 epsilon times this epsilon y1, that would create an order epsilon squared term. And so that's getting dumped into the plus ... category for now. Okay, so again, what we do at this stage is say this is supposed to be true for all epsilon. So equating the like powers of epsilon now gives us a series of a collection of differential equations. The order 1 equation we get by reading off this term, order 1 meaning it has no epsilon in it, and this one doesn't either. So the order 1 ODE is y0 double prime is minus 1. And we should probably remember what the initial conditions are for this y0 problem. We wrote them down earlier. They would be this condition on the first derivative and this condition on y0 itself. So I have initial conditions like this. If I've done that right, I think I have. Yeah. Okay. I guess while I'm there, why don't I just solve that? Or I don't know. I mean, it's unclear what to do first. The other option would be I could just read off my coefficients. I mean, my order epsilon stuff. This is being matched by this. You can see something kind of interesting about the structure here, that to solve this circled blue problem, I'm going to have y1 double prime. It's going to depend on y0. And so that's being solved at an earlier stage. There's a kind of recursive, I don't know, recursive is the word, a sequential character to these problems that often comes up in perturbation theory. So I'll just write down what the order epsilon equation will be, but we won't solve it just yet because we're going to need the order 1 anyway to deal with it. So at order epsilon, we would get, reading off the stuff in blue, y1 double prime, canceling out the epsilons, is going to be 2 times y0. Right, that's the equation at the next order. And its initial conditions, well, those are the initial conditions on y1, which I wrote down here and here. All right, so those are both 0 initial conditions. So y1 at 0 is 0, and y1 prime at 0 is 0. Okay, now it's just cleaning up. We just have to solve these little constant coefficient ordinary differential equations. So solving at order 1, you have to integrate twice. We'll end up getting y0 of tau is, maybe I should just, well, all right, you know how to do that. It's going to be minus a half tau squared plus some constant C1 tau plus some other constant C2. And I can evaluate those by using the initial conditions. So y0 at 0, we said should be 0. That's my C2. And y prime at 0, that's going to be, let's see, that's minus tau plus C1 evaluated at tau equals 0. So that's just C1. And that's supposed to equal, sorry, it's y0 prime at 0. That's supposed to be 1, we said above. So we're getting that C2 is 0 and C1 is 1. And so I've derived that y0 of tau is minus a half tau squared plus tau. So this is all dimensionless. It looks a little bit weird if you're used to the more physical version of this. But the way you should think of it is this is just the counterpart of minus a half gt squared plus v0t. If we were back in the dimensional form, this would be telling us what x is as a function of t. So you can see that has a lot more constants in it than what I've written. But anyway, so there's y0 of tau. This is the classic solution. But now we're well set up to get the correction to that through our perturbation method. And so to do that, we have to write out what is y1. All right, so now we have to cope with this equation. All right, so going back to that then, oops, I still need another page. Let me insert a page here. Okay, let's solve the Y1 problem. So we have at order epsilon, we wrote earlier this, Y1 double prime is 2Y0. Y1 double prime is 2Y0. Now I've just calculated Y0. So I multiplied 2 times the thing above that I've just written in the box for Y0. And so this becomes minus tau squared plus 2 tau. So integrating that once gives me Y1 prime is minus tau cubed over 3 plus tau squared plus something that we can interpret as Y1 prime at time tau equals 0. That would be the constant of integration. And we know that this is 0 because we wrote that down above. It inherited that from the original initial condition. So that's good. We don't have to include that term. It's 0. And so we're left with just minus a third tau cubed plus tau squared. Okay, now integrating that one more time, we get Y1 itself. And so that gives me Y1 of tau is, well, let's see. So integrating the tau cubed would give me tau to the 4th over 4. So it looks like I'm getting minus 1/12 tau to the 4th, and then integrating the tau squared gives me a tau cubed over 3. And then I'd have plus Y1 at time tau equals 0. But we already know that this is 0 as well because we wrote that down earlier. So there it is. We have now calculated Y1 of tau. So let me summarize. Y1 of tau is, let's put the lower order power first, 1/3 tau cubed minus 1/12 tau to the 4th. Very nifty. Okay, still with me on that? All right, good. Okay, you can see perturbation theory involves a lot of writing. Often you would do this in the computer in Mathematica or whatever, but obviously I just want to show you the steps this time through. All right, so now we can put everything together and get our answer. Our classical solution for the altitude plus the first correction term is Y0 plus epsilon Y1, which, and then plus the stuff we neglected. It's coming out to be, in this dimensionless framework, tau minus tau squared over 2. That was my Y0 solution. Then plus epsilon times tau cubed over 3 minus tau to the 4th over 12 plus dot, dot, dot. And so now we just have to see, what does that look like? And also you might remember initially I asked the question, when will this rocket return to the Earth? What is the correction to the classic result that we would have expected? So to see that, Well, let's sort of sketch what we've got going on here. As a function of tau, I would expect this, well, the original, the 0th order behavior we saw as just a parabola like that. And in these dimensionless units, it's going to hit at time tau equals 2. Remember, I chose the characteristic time scale to be halfway through the motion. So that's why we're seeing a 2 rather than a 1. Anyway, so a 2. And this would be the Y0 solution. Look qualitatively like that. And also it would reach a max of 1/2, which was half of the characteristic, or sorry, the characteristic scale was chosen in such a way that this max would be a half. So this is Y. But now what's going to happen when we take into account that we've got this slight weakening of gravity as we go up? You might think about it intuitively. As the rocket goes up and gravity pulls on it more and more weakly, it's going to tend to go higher than it would have otherwise. And then it's also going to be pulled back with less gravitational acceleration. So everything is going to conspire to make it take longer to hit the ground. And actually that is correct. What you would find when you add in this correction term, small correction term, is that the new curve is going to look pretty much like the old curve. But, excuse me, let me use a different color for clarity. It's going to look something like that. It's going to hit a little bit later. And we could, we were interested in what is this new time? How much extra is taken? So we could estimate that. Let's call this time tau star when it hits. This, by the way, is an algebraic perturbation theory problem now, right? This is like what we did in the last lecture. So this is why we did that kind of thing in the last lecture. If you want to know when is y of tau equal to 0 when we return to the ground, well, we're solving, of course, a tau equals 0, that's one place. But what's this? We can get that by solving this expression equals 0 and solve it with a perturbation series to look for tau that is 2 plus some order epsilon correction to make tau star. So let's just plug that in and see what we get. If we write, let me let tau star equal 2 plus epsilon, and then a term tau 1 star plus order epsilon squared. If you plug that in, and then do the same shenanigans with, equating like powers of epsilon and all that. I'll skip the algebra here because we did that kind of thing last time. You'll find that you get tau 1 star comes out to be 4/3. So that we end up getting tau star, our prediction from perturbation theory is tau star should be 2 plus 4/3 epsilon plus higher order junk. Or if you want to see it in the original dimensional form, it would come out like this. You would get T star is the classical result, 2v0 over g. But then there would be a correction term, which is going to come out to be 4/3 v0 squared over g squared r. Lots of constants in there. And that is, of course, a small term because of the enormous radius of the Earth compared to the height of the projectile. So I'll let you check the details on that. But what I want to show next is this any good? And of course it is good, that's why I'm doing this. Here's Mathematica's plot of y0, the unperturbed solution, as we would say, the classic solution in blue. And then in orange, you're seeing what I sketched above. This is actually the y0 plus epsilon y1. I think I used here an epsilon of, to make this graph before the lecture, I used an epsilon of 0.1. And what's interesting is that if that's, I think that is what I did, that would predict in these dimensionless units that I should be getting, I set up here, I was expecting tau star is 4/3, 2 plus 4/3 epsilon. So I should be getting down here 2 plus 4/3 times 1/10, that's my epsilon. So that's 2 plus 4 over 30. That's 2 plus 2 over 15. That comes out to be around 2.13. And I mention that because if you zoom in on this picture, you can see here's 2.1, here's 2.2. That's pretty close to 2.13. So perturbation theory is really working here as it should. Regular perturbation theory is telling us, you know, like I say, the leading correction to the traditional problem. Okay, so maybe that's enough about that. Okay, next I would like to do an example to illustrate some theoretical points about how perturbation theory works, regular perturbation theory. So this example is not a particularly scintillating example. It's, I just want to run through it because I want to make certain points about convergence and some other theoretical comments that will come up a lot in the rest of the course. So I've written it all out ahead of time because it's sort of tedious, but let me just try to walk you through it. All right, so here we're being asked to solve yet another nonlinear differential equation. It's got this y² term in it, but it's got also a small parameter, epsilon. And so it's first order, only a first derivative here. We're solving it with the initial condition y of 0 equals 1. Let's solve it for all x, or positive x, not negative x. As before, I'm going to neglect the order epsilon squared terms. And I just want to focus on these theoretical points about convergence and also about something called uniformly valid solution. That's an idea we're building up to. What does that mean? All right, so we could grind out the solution to this very similarly to what we just did with the projectile problem. And so I'm going to kind of blaze through it. Again, we could try a regular perturbation series in powers of epsilon, y0 of x, y1 of x being those coefficients. We could convert the initial condition y0 equals 1 into conditions on the y0 and the y1 functions, very similar to what we did above. We would get this. Here we only have one initial condition per order of epsilon because it's only a first order equation. And so our ODE, when we plug it in, well, here we are plugging in the series for y prime, and here we are plugging it in for y, and then for epsilon times y². So we put that in there, expand everything out, and discard anything that is order epsilon squared. So that's why I have dot, dot, dot here and here. And in this case, when I square this expression, notice I get y0 squared from here. The next term I would get in order of epsilon would be a y0 times an epsilon y1 times 2. That whole thing would be order epsilon, but then times this epsilon would make order epsilon squared, and that's what we're neglecting. So I don't even need that cross term or any of the other terms. I only have to keep this much to the order that I'm working at. Okay, so doing that, then I get two equations. I have an order 1 equation, which I get from looking at this y0 prime, this y0, it's matching up against 0. So that gives me this. There's my initial condition at that order. The order epsilon terms I get from here, and from this term, epsilon times y0. And, I'm sorry, epsilon times y0 squared, I should say. Right, because this whole thing is inside a square. All right, so at order epsilon, I've got this. I already read off its initial condition, and now I solve each of those little problems, solve them sequentially, just like we did a minute ago. And what we get is at order 1, we would get e to the minus x using this initial condition. And then substituting that y0 in here, this equation becomes y1 prime plus y1 is negative y0 squared, which becomes this minus e to the minus 2x. And it inherited this initial condition, y1 of 0 is 0. Okay, so then we have to solve that. It's a little bit harder, but not much. Notice it's still just a constant coefficient linear differential equation. So using the homogeneous plus particular method of solving those kind of things, we end up getting this for y1 of x. Okay, so putting all that together, now I'm getting to my point, I would get this expression for my approximation for y, taking two terms in the perturbation series. There it is, plus the stuff I'm neglecting. Okay, now why am I doing all this stuff? Because I want to address the question, in what sense is this really an approximation to the right answer? Sorry, the clouds keep coming in and going out today, so I'm changing the lighting. To what extent is this a decent approximation? Well, we could ask, like you've been brainwashed to do in your, the first time you ever deal with power series, you always think about convergence. So does this series converge with respect to epsilon? Okay, we could ask that question. You can probably already guess what might happen given earlier things in the course. Actually, here it is going to converge in epsilon. I mean, ordinarily we wouldn't know in a problem like this because it's too hard to deal with the series. But here we can actually see that it's going to converge if epsilon is small enough, because I did a contrived and tricky thing, which was I posed a problem that has an exact solution that I can write down. This differential equation, although it's nonlinear, yeah, it's nonlinear, but come on, it's only first order and it is separable. We can just separate variables and integrate both sides. This is something you could do in a first calculus course. So in fact, it's quite easy to solve. So if you solve it by separation of variables, you end up getting this exact solution shown in the red box. And this is a game we will often play in perturbation theory. To calibrate our methods, we'll solve problems where we happen to know the exact answer, just so then we can compare how well is perturbation theory doing compared to exact results. It gives us a feeling for problems when we won't be able to find exact results. We'll at least have some sense of how well this might work. Anyway, so here we do have the exact result. And now if I think about this expression in the red box, think about it for x being constant. Just fix x and regard this as a function of epsilon. It's the epsilon dependence we're interested in. So think about x as like a parameter if you want, and epsilon is the variable of interest. Regarding the x as fixed in this expression, then think about expanding this as a Taylor series in epsilon. Really, I guess I should say Maclaurin series, because I'm expanding around epsilon equals 0. So if I expand that as a Taylor series, well, when will that Taylor series converge? So in complex analysis, we answer a question like that. We show that this will have a convergent Taylor series expansion in any disk about epsilon equals 0, the origin in the complex epsilon plane. Kind of weird if you're not used to thinking of this. Instead of thinking of epsilon as a small positive number, now just think of it as a complex number. Because that's really where power series should be thought of, in the complex plane. So ask, in the complex epsilon plane, where does this series converge as a series in epsilon? And in complex analysis, we show that it converges inside of a disk around the origin. This is the disk of convergence. It's for all epsilons less than a certain radius of convergence, where the radius is given by the distance from the origin to the nearest singularity of the function, regarded as a function of epsilon in the epsilon plane. So that's what causes a breakdown of convergence when we bang into a singularity as we're swelling out this disk of convergence. When it bangs into something singular, that's as far as we can go in expanding the radius of convergence. So where is this singularity that I'm talking about? Well, look at this expression again. You can see that we could potentially be dividing by 0 down here. So when that occurs, we have a singularity. And so when we divide by 0, that would occur when this condition is satisfied. That's when the denominator is 0. And you can solve that for epsilon. Remember, x we're thinking of as some fixed number, just some parameter. So this tells us how big an epsilon we can tolerate before we lose convergence. And the answer depends on the x that we're interested in. You can see through that explicit formula. But just to give you a feeling for it, suppose x was 10. If x is 10, then the epsilon singular, that's the biggest epsilon we can get, would be of the order of epsilon, not order, it's epsilon to the 10th over 1 minus epsilon to the 10th. In the complex plane, this is a number very close to -1 because e to the 10th is a big number. The 1 will be kind of negligible. It's actually a little bit less than -1 in the sense that it is more negative than -1. So if you draw it in the complex plane, in the epsilon plane, you'd have this disk of radius 1 that is safe. It has not hit the nearest singularity. So you have convergence for any epsilon less than 1, actually any epsilon less than 1 in magnitude, or even less than this quantity in magnitude. We could push out a little farther if we want. Okay, but why am I dwelling on this? Because I want to make the point that now forget about x equals 10, use any x, any positive x. For any x greater than or equal to 0, the biggest that epsilon singular, or the worst case, is 1 in radius. What I'm trying to say is any epsilon less than 1 in magnitude will give us convergence of this series. So that's what I've written as the upshot. Okay, so you'd sort of instinctively think that the series expansion that we did should work for small epsilon. We're now saying rigorously, in fact, the series will converge for any epsilon less than 1, no matter what x we're studying. So that should give you some confidence in this perturbation series. It does converge, provably does converge. And yet, I hope by now in this course you realize that convergence is the wrong issue to worry about, because we're not interested in taking infinitely many terms in the series. We never do that. I mean, well, almost, essentially never. In fact, we do the opposite. We tend to take very few terms in the series. We take maybe 1 or 2 terms, typically. So convergence is beside the point. The real question is, do we have an asymptotic approximation of the right answer? That's what we really care about. So that's what I'm saying here, that convergence is the wrong issue to worry about. Suppose we just take 2 terms, like we did. Compare the approximation we get if we do y0 plus epsilon y1 to our exact result. And let's take a pretty hefty epsilon of 0.5. How good is this? Well, all right, here's Mathematica's answer. The exact result is shown in blue. That's that curve. The first approximation, the leading one, is shown here in orange. It's qualitatively getting the right stuff. It's not so quantitatively accurate, but then again, epsilon is pretty big. Still, if I just take one correction term, the epsilon y1 term, that's the green, you can see it's really hugging the blue pretty well. I mean, I made a difference just so that you could see the difference by picking epsilon pretty big. But I hope this is convincing you that even 2 terms can give you a very decent approximation, and for a substantial epsilon. on a problem like this. The other thing I want you to notice is that the approximation is very good over the whole range of x that we're looking at. It's not like it's good at some x's and bad at others. It's working for every x. And that's what I want to talk about next, the concept of a uniform approximation that works well for all x's in the domain of interest. So these are the important issues then, not convergence, but first of all, that the series that we write down in such a problem, typically if we had n terms, it would look like this, that such a series is asymptotic to the exact solution. That's what we want. And our methods in regular perturbation theory will give us such a thing. Asymptotic was already defined back way long ago in lecture 2. So remind yourself what it means for a series to be asymptotic to a function. But here's the new concept. This series is not just asymptotic to the desired result, it's uniformly valid. So this has a technical meaning, but basically it means what you're seeing in this picture, that it's working well at all x, and it gets better as we make epsilon smaller. And it does so in a uniform way with respect to x. So here's the official way of saying that. Pick some delta greater than 0. Think of it as a very small number, like a tolerance. It's how much relative error can we tolerate. So no matter how tight we want to make that relative error, there exists a number r, which is going to be a number that controls how big our epsilon can be. It's like a radius of not of convergence, but a radius for having uniform validity. So given any delta, there exists an r, the key being that this r is independent of the x in the domain, such that the relative error in our approximation, that is y minus the approximation compared to the approximation itself. So the percentage error, the relative error, can be controlled to always be less than or equal to delta. And that is true for all x. We can get within, say, 1% or 0.1% for all x, as long as we make epsilon small enough, less than this r. So if there exists an r with this property, I mean, it's a big mouthful, right? It's all these quantifiers. But what it basically says is that the relative error can be made small everywhere just by picking epsilon small enough. And that's the key thing. One epsilon works for all the x's. There's no bad x's. Okay, one epsilon does the trick for all of them. That is what is typical of regular perturbation problems, as opposed to what we're going to study in the rest of the course, singular perturbation problems where there are bad x's. So I've got about 6 minutes left. Let me try to give you a feeling in those closing few minutes, what could go wrong? I mean, regular perturbation theory is sort of the best of all possible worlds, and so we're not going to spend much time on it. We want to look at the richer, juicier, nastier problems that are singular. Okay, so the opposite situation, what is it that could go wrong when we don't have regular perturbation theory working? Well, sometimes we have an approximation that's asymptotic, but not uniformly valid. There are bad x's. And so here's an example of such a thing. We'll be spending several lectures on this in the next few lectures. So example 3, suppose I'm just looking at a function like this. Let's consider this function. F of x and epsilon is the function x plus e to the minus x over epsilon. Consider this guy. Now, why that? Well, here I should say, I want to think about my x as being a number between 0 and 1. And here I'm being strict about my less than signs. I want it to be x to be strictly greater than 0, not equal to 0. So x is strictly greater than 0, but less than 1. And I'm interested in thinking about this as epsilon goes to 0. And you can check that for this f that I'm writing down, this f of x is simply asymptotic to x as epsilon goes to 0. Let's think about it going to 0 from the positive side. Right? In other words, x is a perfectly good asymptotic approximation to f as epsilon goes to 0. And it's, you'll recognize this term is one of our transcendentally small terms as epsilon goes to 0 for any fixed x. So this looks good. And yet, even though we have an asymptotic approximation to f, here's what it looks like. The asymptotic approximation, x is shown as the line, the orange line. The asymptotic this function, x plus e to the minus x over epsilon, it's really working beautifully out here. They're on top of each other. The blue is on top of the orange, but you'll see there's something bad happening down here, where there's a big departure. I've used epsilon of 0.05 in this example. And right when you get to around that scale, like here's 0.1, but maybe I should mark it. I mean, this would be 0.1, 0.5 is here, 0.5. I mean, you can see you're really getting into trouble. You're like sort of in the middle of trouble there when x is around epsilon. And once x is around epsilon, then you're starting to have trouble. You can see because in this expression, that term is now of order 1 and the e is no longer, that old term is not negligible anymore. So this is the problem. You can see that close to x equals 0, something is breaking down. And that's what I meant about there being bad x's. This problem, although we have an asymptotic approximation, we don't have a uniformly valid one. We're getting a breakdown near the left end of the interval. And so that's the issue. I've set it a timer for myself. I still got 2 minutes left. I don't want it to go off and shock me. Well, okay, so what if it does? I mean, you can see what the issue is. If I wanted to get a good approximation, it sort of depends on what x I'm interested in approximating. There's no single epsilon that works well for all x's. Like, to be very concrete about it, let me say it this way. To get a good approximation at, say, x equals 10 to the minus 2, you're going to need to take an epsilon that's much less than 10 to the minus 2. And then suppose you wanted to get even closer to the left endpoint. If you wanted to get a good approximation at x equals 10 to the minus 3, well, you're going to have to make epsilon smaller still. Now you're going to need epsilon much less than 10 to the minus 3. And so you can see the problem here. There's no single epsilon that's going to work for all x's in this open interval from 0, say, to 1. So that's the breakdown of the uniformity approximation. And when this kind of phenomenon happens, we have what's called a boundary layer, where something else is going on. And so we're going to talk next time about how to deal with problems that have boundary layers, and that'll keep us going for a few lectures. They're very important in fluid dynamics, many other subjects as well. All right, so I look forward to discussing those with you next time.